right, in this podcast, we're going to talk about the VSEPR theory and molecular geometry. All right, so when we draw Lewis structures, they don't really show us geometry. They only show us the electron pair placement. So they're like two-dimensional structures, basically. So we have to look at VSEPR to tell us what they look like in real life, in 3D. It's pronounced VSEPR, but it stands for valence shell electron pair repulsion. Basically, it attempts to explain the 3D shapes of molecules based on the fact that electron pairs and lone pairs want to be as far apart as possible. So, once you know the geometry, you can actually draw 3D sketches with these little wedges and these little dashes and whatnot. So the dashes are telling us that they're going into the page, and the wedges are saying they're coming out of the page, whereas the ones that are regular are on in the same plane as the page. All right, for the formula we're going to be looking at, we're going to use the AXE model, which means that A stands for our central atom, X is going to stand for our outer atoms that are attached to the central atom, and E is going to be our lone pairs of electrons that are on the central atom only. So this is all based on the central atom. So this is a sheet that you should have gotten. On here, it is slightly different. Here, it's electron pairs and bonded pairs. Okay, and I'm going to explain that in a second. All right, so we want to look at the number of domains, basically, to be able to tell the electron geometry. So electron domains are anything that is attached to the central atom, be they a bond or a lone pair. If it's attached to the central atom, it counts as a electron domain. So you count your electron domains first, and then you want to look at how many of them are bonded to the central and how many of them are lone pairs attached to the central. Okay? All right, so we're going to look at the 2 electron domain first. So that would be as if we had one bond attached to the central with or without a lone pair. So this is something that a lot of students struggle with when they're thinking about this. But basically what you have is I've got this simulator here that I'm going to be showing you guys stuff off of where you can see the molecular geometry and the electron geometry, and you can add and subtract lone pairs and such. So here we go. We have a central atom that is purple, and then we have a bonded atom. And you see no matter which way you swing this sucker, it continues to have a 180-degree bond angle. So it stays linear no matter what. All right, now the next possibility is if we have a still 2 electron domain, but this time we have 2 bonds attached to the central, 2 bonded atoms. Okay, so if you have that, 2 bonds attached to the central atom, no matter which way you swing them, in order for them to be as far apart as possible, they are going to maintain a 180-degree bond angle. So they're always going to have a linear molecular geometry and a linear electron geometry. All right, next we're going to look at the 3 electron domain region. So in the 3 electron domain region, you see that we have 2 possibilities. We either have all 3 are bonded pairs, or we have 2 bonded pairs and 1 lone pair. If we have 3 bonded pairs, it is called trigonal planar or trigonal. Sometimes you'll see it called either. Mostly the AP exam calls it trigonal. So if you look at this video here, you can see that it's turning no matter which way you look at it. They're all staying 120 degrees apart. So this is a trigonal geometry, trigonal planar. All right, now if you swap one of those, swap one of the atoms out for the bonded atoms, out for lone pairs, you're going to be in the bent region here, okay, which is going to have less than a 120-degree bond between the bond angles. Okay. All right, next is going to be our 4 electron domain. 4 electron domain, you have 4 possibilities. These are called tetrahedral electron geometries. Okay, now if there are 4 bonds, then it's also a tetrahedral molecular geometry, which has a 109.5 degree bond angle. And here you can see a video of it in the works. So I kind of think of it like a little tripod with one sticking up, but they're all 109.5 degrees apart. All right, now if you replace one of those bonded pairs with a lone pair on the central atom, you end up with this AB3E or AX3E. This is called a trigonal or a trigonal pyramidal or a pyramidal. Oops, didn't mean to do that. But basically, this is going to look very similar to the tetrahedral, except now that top lobe is a lone pair. So you still have the 3 bases of the pyramid, but then you have the lone pair on top. Next is if you have 2 bonded pairs and 2 lone pairs. This is going to give us a bent electron geometry. So here is this, the most popular molecule in the world. It looks like this. It's called water, H2O. 2 lone pairs on the oxygen, and then the 2 hydrogens coming off. Bent geometry. Next you have this AX5, which is your 5 electron domains. Here you have 4 possibilities. So it's called trigonal bipyramidal. So if you have 5 bonds just straight coming off, you see it has a little bit of a different kind of shape. Most of the time people have a harder time imagining what this one looks like in 3D. But basically you have these 3 that are on like a trigonal sort of plane all together, and they're all 120 degrees apart. And then you have 2 that are sticking straight up and straight down from that, which are 90 degrees away from all the rest. So that's kind of how I think of it. All right, now if you take one of those bonds off and make it an alone pair, you end up with the seesaw. Seesaw is one that people have a hard time understanding as well, but if you think about that, still that 3 electrons on one plane, or 3 bonds on one plane, take one of them and make them a lone pair, and the other 2 are still bonded pairs, and then you still have the one sticking up and sticking down, and that is what seesaw looks like. All right, next is if you have 3 bonds and 2 lone pairs. This one is called T-shaped. It looks exactly like a T. So now this time on that central plane there where you have 3, 2 of them now are lone pairs, and you have the one sticking out by himself, and you still have the 2 up and down, so it literally looks like a T. That's why it's called T-shaped. All right, and then if you have only 2 bonds and 3 lone pairs, you end up back at linear, basically. So all 3 that are on the same plane are all electron pairs now, and then the ones sticking up and sticking down are your bonded pair, and so it's a linear electron geometry. All right, the last category that we have to look at are the 6 domain pairs. For some reason, they're called octahedral. Don't really know where that decision came from. But if you have all 6 of them that are bonds sticking off of that central atom, it is what we call octahedral. I kind of think of it as having 4 that are on one plane, like a square planar, and then 1 sticking up and sticking down from that. So there you get your 6. They're all 90 degrees apart. Now if you take one of those bonds and you make it a lone pair, you end up with what we call square pyramidal. So square pyramidal, you take 1 off from the one that is sticking up and sticking down. You still have your 4 on the central plane, and then you have one of the ones that was sticking up is now a lone pair, and the other one sticking down. So it's like you have 4 bases of the pyramid in a square, and then you have the top of the pyramid. So square pyramidal. All right, if you have 2 lone pairs and 4 bonded pairs, it's what we call square planar. This time, all of the ones that are on the that central plane, all the 4 of those are bonds, and then the lone pairs are sticking up and sticking down. So this is a square planar once again. All right, and then there are two more options that aren't listed on your chart, but I thought I'd go over anyways. This is if you have 3 bonded pair and 3 lone pair. This is another version of the T-shaped, as you can see. And then the last option is if you have 4 lone pairs and 2 bonds, you end up with linear all over again. Okay, so these last two are kind of rare, but just wanted you to be aware that they're out there. All right, so what happens if you had multiple bonds instead of just these single bonds? How does that affect our geometry? So you see right now we have 3 single bonds, and we have trigonal planar geometry, both in the electron domains and the molecular geometry. And now we start adding, double bonds, double bond, another double bond, okay? And I hope you realize that the electron and molecular geometry are not changing at all. So double bonds and triple bonds don't change your electron domains. Okay, they don't change your molecular geometry. They're still treated as just one bonding domain. All right, now bond angles. All right, so you got bond angles here. Here's just a couple of them. So linears 180, trigonals 120, tetrahedrals 109.5, and then you've got 120 between the trigonal on the trigonal bipyramidal, and then 90 between that upper lower plane and the middle plane. And then on the octahedral, they're all 90s. Now, when you put lone pairs, what they do is they actually push the bonded pairs down. So, like if you look at these two examples, you see that they're both trigonal planar electron geometries, but once you throw that lone pair on top instead of that extra bonded oxygen, what you end up with is you end up with a smaller bond angle there, because that electron pair is actually pushing those two bonds further away from itself and therefore closer together. If you don't have a central atom, sometimes you might have multiple central atoms. You can still predict geometries of each angle. You're just going to have to do it piece by piece. You're going to have to look at each central atom separately. And how well does this model work? Well, it gives us a pretty good understanding for such a simple model. Our predictions are almost always right, but there are some exceptions. For one thing, this model does not deal with the odd electrons that you're going to see in a lot of nitrogen compounds.